Today I'm going to tell you a little bit about our micromodular devices that were originally developed at Legacy Linear Technology and are now part of ADI's power product portfolio. So here's the agenda for today's talk. I will introduce you to what a micromodule regulator is and how it's constructed and describe what problems it solves. Next, I will demonstrate their quality and reliability, since even though they are constructed with many parts, we test the micromodules as if they're an IC. From here, I will cover what we see as the packaging trends within this product line, in which it will become clear what we are putting together for even greater power densities and functionality into what is a shrinking form factor. Next, I will cover the micromodule regulator's thermal performance, since this is always an area of great concern. From there, I will give you an overview of the micromodule product portfolio. Here I will cover micromodules from single-digit amps to hundreds of amps. Furthermore, I will cover our ultra-thin versions for the use on the backside of printed circuit boards, as well as our dual, triple, and quad output versions that enable even greater utilization of the PCB area. I will also show you areas where our micromodules have been used in many large digital chip suppliers as part of their reference designs. And lastly, I will talk about how we have incorporated power system management into our micromodule regulators as well. Okay, so what is a micromodule regulator and why did we decide to make them? Well, as you can see from the cutaway drawing, a micromodule device resembles a surface mount IC. However, they also include all the necessary support components that would normally be used to construct a power conversion circuit. This includes a DC to DC controller, MOSFET dice, magnetics, capacitors, and resistors, and so on, all mounted on a thermally efficient laminate substrate. They are then encapsulated using a plastic mold cap. The result is a complete power supply that can be simply adhered to a printed circuit board. Built to the industry's highest quality standards, this product family dramatically reduces risk, time, and effort to successfully design high-performance, high-power density solutions. It is as if we have taken all our power supply expertise and know-how and put it into an IC-like form factor. I am sad to say this, but for those of you who have had time constraints for designing power conversion circuits, and they're going into mass production within weeks, and have had to spend many late nights debugging your supplies early into the wee hours of the morning, these times are over if you use these micromodule regulators. In this slide, we are going to take a closer look at the internal construction of a typical micromodule product. The package options are land grid arrays and ball grid arrays. The BGA is offered in lead-free and tin lead versions. You can also see the internal components needed to form a switch mode power conversion circuit. Some are in die form, while others are finished packaged products. Nevertheless, these components are all mounted onto a bismolide trizene laminate substrate, which has excellent electrical and thermal properties. By the way, we use BT as a short form for bismolide trizene, and I think you can understand why. A micromodule product is not just about integration, however. It provides other properties and performance characteristics over some of the competing alternatives. Okay, I think you now have a reasonable understanding of what a micromodule product is and how it is constructed. So a reasonable question might be, what problem are we trying to solve with this type of product? Well, apart from the fact that we did not have enough internal resources to design every single power supply our customers wanted, we realized that power supply design expertise is actually declining on a global basis. Furthermore, while this is happening, PCB area is now at a premium. Everyone is trying to put even more functionality and capability into an ever-shrinking form factor. As if this is not bad enough by itself, thermal design constraints are now more complex as designers try to pack more capability into smaller space while delivering more power in an environment that has limited heat sinking or airflow for cooling purposes. Finally, as I am sure most of you already know, time to market pressures are intense. The power supply is one of the last items to be designed in a system, and mass production starts are usually just weeks away. Okay, let's take a closer look at the declining power supply design expertise in the industry. First, the average age of a degreed engineer is 57 years of age, and this is a global average, with China having the youngest average. Regardless, the clear majority are facing retirement in less than a decade. So what are the top three concerns of these engineers? Well, the first is insufficient people to get the job done. Second is finding the optimal components for their design. And then third, time to market pressures. Okay. I do not need to tell you that PCB area is at a premium. You already know this from your own experience. Take any datacom or telecom board, for example. It is laden with many digital processors, ASICs, memory, and so on. All these need to be powered while voltage levels are varying from just north of 5 volts down to as low as 0.6 and even 0.5 volts after some intermediate bus voltage, which can vary somewhere between 12 and 48 volts. At the same time, system designers are continually being asked to pack more functionality into these ever-shrinking form factors. Thermal design constraints are becoming more severe. As more and more functionality is packed onto the PCB, the overall power levels needed are increasing. Meanwhile, cooling is also at a premium due to heat sinking space constraints or even limited airflow. This is a headache for the designer since he has maximum internal ambient temperature constraints in his system, and he cannot violate these without compromising the performance or even the long-term reliability. If only I had a nickel for every time I have heard someone mention time to market pressures, I'd be a rich man. But seriously, time to market pressures have increased dramatically in recent years due to both competitive pressures and the need for faster revenue streams. So the power supply designer is under the gun for getting his power conversion circuits designed and functional in weeks, if not days. And that nicely segues into the topic of this presentation, simple and done power supplies, otherwise known as micromodule regulators. Simply put, micromodule products provide a simple and done, proven power conversion solution. So use them and say goodbye to all those late nights of debugging supplies in the lab. So it goes without saying that we have implemented a rigorous ongoing quality and reliability process for our micromodule products to ensure long operational life once they have been deployed in end systems. This slide provides a summary of the testing and the data that we have accumulated since the introduction of our first product, which was the LTM 4600, way back in October of 2005. So as you can see, this includes over 22 million power cycles, over 5 million device hours of hot temperature operational life, over 2 million hours mounted temp cycles to ensure that these modules can operate 24/7, 365 days a year for a decade without having any intermittent contact issues from the package leads to the printed circuit board. Over 25 million temp cycles from negative 65 C to plus 50 degrees C. Over 16 million thermal shocks from negative 65 C to plus 150 C. And this is liquid to liquid on a finished power supply. The end outcome is a fit rate, failure rates in time, of less than 0.4. To put this in perspective, this equates to 0.4 device failures in every billion device hours of operation. And that's on a complete power supply. Even our closest competitors' integrated circuits, that's silicon in a package, have higher fit rates. By the way, we continually update this data on our website, so be sure to visit our website for the most current information. Finally, we have second sources for mechanical assembly and manufacturing, as well as multiple sources on substrates and internal components. And we carry a very large die bank, usually six months or more, so guaranteeing continuity of supply is not an issue. Okay, let's take a closer look at the micromodule packaging options. When we first introduced the LTM4600 way back in October of 2005, we used a land grid array, otherwise known as LGA package option. The thinking at the time was that since a lot of large digital ICs were using similar LGA form factors, it would be easy for the users to use our micromodule products. Well, this wasn't true all of the time, only some of the time. Therefore, we decided that having a ball grid array, BGA package option, would also be a good idea too. This turned out to be fortuitous for two reasons. First, it was easiest for our users to not only go into high volume production with LGAs, but secondly, it was easier to put solder balls on the round pads. Moreover, it allows for both leaded and lead-free solder balls, and since many of our micromodule device users are in the aerospace and military market segments, they were very happy about this. All right, now I want to give you some deeper insight as to what has been driving some of our packaging trends since the inception of our micromodule product line. By the way, did I mention that we currently have over 100 different micromodule regulators? So, the first part we introduced in this product category was the LTM4600. It was a 4.5 volt to 20 volt input capable device with outputs going from a high of 5.5 down to 0.6 volts with up to 10 amps of continuous output current. It was in a 15 millimeter by 15 millimeter by 2.82 millimeter surface mount LGA package. Its killer app at the time was 12 volts to 3 volts at 10 amps with 90% efficiency. And remember, this was back in October of 2005, well over a decade ago. So this level of performance was groundbreaking stuff at that time. As you might have already guessed, one of our key metrics was to improve the micromodule's thermal performance so that we could increase its output current density while remaining in this same 15 by 15 millimeter footprint. Since this was clearly a significant thermal issue, we needed to address getting the heat generated by its operation out of the package. I'm told by our designers that since they had anticipated these issues, this is one of the reasons why they had used the bismuthide triazine laminate substrate, because it had excellent thermal properties and facilitated taking heat through the bottom of the micromodule and into the PCB where it could be dissipated. Well, to be frank, that was okay in the mid-2000s. However, by the time another 5 or so years went by, our customer base told us that they could no longer dissipate the majority of the heat through their PCB. Instead, it needed to be able to pull heat out of the top of the package and dissipate it into the air. Therefore, we designed a special heatsink that was encapsulated inside the package and connected to the top of the internal MOSFETs and inductors. This heat sinking was exposed on the top side of the micromodule. As a result, the user could add their own heat sink on top of the micromodule to improve pulling heat out of the top, or if they had 200 or more linear feet per minute of airflow, this also facilitated better thermal performance. Truly a win-win situation. As a result, we continued to evolve and developed micromodules with inductors on top, since this acted as a heatsink to further improve thermal dissipation qualities. As you can see from the slide, we have added further enhancements since then. Finally, I must mention why we introduced our ultra-thin micromodules. We realized that in many cases our customers would only utilize the underside of their PCBs with discrete components due to space limitations there. So it turns out that many rack-mounted systems, there's only a 2.2 millimeter of height available to mount components on this underside. So we developed micromodules with 1.9 and in some cases 1.8 millimeter maximum heights so that they could easily fit there to help with space density issues. Now, the background that I've just covered on the previous slide will make it straightforward for you to understand what is going on in this thermal performance slide. This can be thought of as an evolutionary slide on how we have been able to continuously improve our micromodule thermal performance from inception through to some of our current offerings, a decade-plus long journey. So for those of you not familiar with thermal imaging photography, what you are seeing on this slide are images of several types of micromodule regulators with varying types of construction, with the goal of increasing the device's ability to pull heat out of the top of the micromodule device and into the free air, where it can facilitate additional cooling from airflow within the system, or could have an additional heatsink that is shared with digital FPGAs or GPUs that are usually present in these types of systems. So, color blue shows low temperature or minimal power dissipation, and colors orange through red are elevated temperatures in high power dissipation. Of course, this is what we want to occur when we want the heat generated by the power conversion process to be pulled out into the free air and not down into the PCB. So on this slide, I wanted to demonstrate to you how we are increasing the micromodule power density in ever-shrinking form factors. At the bottom of this slide, you can see the LTM4627. It is a 20-volt input device and can deliver 15 amps of output current down to voltages as low as 0.6 volts with an efficiency that is around 90%, depending on the specific V-out to V-in conditions. The LTM4638, which is about to be released in the next couple of months, is a 20-volt device that can deliver 15 amps of output current as low as 0.6 volts with a nominal 86% efficiency. Pretty close. However, volumetrically, the 4638 is 5.6 times smaller than the LTM 4627. And so the point here is that there is only a small delta in the conversion efficiency between these two devices under the same operating conditions, but the footprint and space required for the implementations are orders of magnitude different, and all this improvement has been attained in less than a 4-year time period. And here on this slide now you can see the 4638 in the 6.25 by 6.25 by 0.02 millimeter BGA. That's a dramatic size reduction. Okay, now for something really groundbreaking. In the next 5 slides, I want to cover our journey to a single 100 amp output capable micromodule regulator in a compact form factor with industry-leading performance characteristics. But before I get there, I would like to share with you some of the background on how we got to this point. For a long time, our existing users of high-power micromodule packages kept on asking us for smaller and more efficient and higher current density devices. Some of this feature set might be considered mutually exclusive. Nevertheless, our micromodule regulator design team took this request to heart and began figuring out a way on how to get us there. So, as you can see from the left-hand side of this slide, back in 2003-2006 timeframe, we had micromodule regulators in the 15 millimeter by 15 millimeter footprint that were capable of delivering output currents from 26 amps to 50 amps pretty good. Now, I should state at this point, one of the key matrix criteria for our power modules is to be able the full rated output current from a 12-volt input to a 1-volt output with 90% conversion efficiency. The reason being that dealing with 10% power lost as heat is usually thermally acceptable in most designs. By the way, at the same time, we were looking at new and innovative heat sinking techniques to facilitate getting more heat out of the package. Hence, as we move on into late 2016 with our 40 amp plus micromodule regulators, we have efficiencies in this 88 to 89% range, which is very close to our internal goal. As we move into 2008 beyond, we have micromodule regulators with current outputs in the 80 to 100 amp plus range, and even higher voltage capability and more features. But I'm getting ahead of myself here. We'll talk about that more in later slides. So on this slide, before we could develop a 100 amp micromodule regulator, you know, how did we deliver this level of output current? So you can see clearly here the progression that we were able to make. If I didn't mention it already, many of our high current micromodule regulators are current mode control, and this allows them to easily current share when multi-devices are connected in a polyphase parallel configuration. So some specifics here. In 2010, we would utilize 12 of our LTM 4601s in a polyphase parallel configuration, and this allowed us to deliver 100 amps from a 12-volt input to a 1-volt output. By 2012, we had got this down to using 4 of our LTM 4620s in a polyphase parallel configuration, allowing us to deliver that same 100 amps from 12 to 1 volt, but with a significant size reduction. By 2014, only 3 of our LTM4630s in a polyphase parallel configuration allowed us to deliver 100 amps output from a 12 volt input to a 1 volt output. And by 2016, only 2 of our LTM4650s were required in this polyphase parallel configuration to deliver 100 amp output. And at the same time, we only have a plus or minus 1% total DC error over line load and temperature for that 1 volt output. Pretty impressive stuff. Okay, so here is the 12 times 4601s in more detail in terms of looking at what that size looks in relation to a HB pencil, and you can see where the 4700 is, which we'll release shortly, and I'm going to talk more specifically on that. The size differential there is astounding. So, and not only does this 4700 deliver 100 amps of continuous output current, but it also has power system management capability. So we've got digital telemetry, and I'll talk more about that later on. Okay, so let's talk more specifically about the LTM 4700. And as we move on to slide 18, you can see some more of its key specifications. It's a single 100 amp output capable micromodule device, or it can be used as a dual output with 50 amps per channel. It is very close to 90% conversion efficiency when stepping down from a 12 volt input to a 100 volt output at 100 amps with only 200 LFM of airflow, and has a plus or minus 0.5% maximum DC error over temperature. Its XYZ footprint is 15 millimeters by 22 millimeters by 7.82 millimeters. The expected release for this device is in the July 2018, so that's really not that far away, and samples are usually about 6 to 8 weeks ahead of that. In addition to having a dual 50 amp or 100 amp output, the LTM4700 also incorporates a PM bus with an I2C, I2C interface, or as we call it internally, power system management, and we even abridge it further to simply PSM. So this enables different capabilities. It's easy to configure voltages, to define complex on and off sequencing arrangements, define fault conditions such as overvoltage or undervoltage limits, set important power supply parameters such as switching frequency, current limit, etc., all over a digital communication bus. Over this same communication bus, you can read back important operating parameters such as input voltage, input current, input and output power, internal and external temperatures, and in some of our products even measure the energy consumed. Users can easily implement very precise closed-loop margin testing of their designs, as well as trim power supply voltages to very precise levels. A system benefit of using PSM devices is higher reliability and quality. Our built-in servo loops will maintain higher power supply accuracy over the life of the product, therefore improving reliability. The readback features of our PSM devices can be used to improve test coverage in-circuit test and screen out possible defects or device defects before they get into the field. During the life of a product, our PSM devices continue to monitor important parameters. Trends in voltage, current, and temperature can be used to profile the power system. And once a good system signature can be found, a bad system or one that is about to fail can be easily identified. Finally, if you want to know more about power system management, I encourage you to take the time to see the seminar that I gave on this topic back in December of 2017. Okay, since the LTM 4700 is still a few months out, let's talk about high power scaling with micromodule devices which are currently available. As already mentioned, most of our step-down micromodule devices automatically current share since they are current mode control based. Therefore, to generate a 250 amp output from a 12 volt input down to 1 volts, for example, one can simply use 5 of our 50 amp rated step-down micromodules configured in parallel, as shown on the left-hand side of this slide. Also on the right-hand side of this slide is an example of a 386 amp output configuration for a well-known digital FPGA supplier. And in this case, the solution consists of 7 of the LTM 4650s and a single LTM 4677, which also brings in the power system management. The advantages of this solution, I think, are clear, but let me just tell them. Precise sharing of total output current amongst each micromodule, which minimizes thermal stress, uniform heat distribution, and of course high reliability operation, since there is no thermal stress on a single device. I would now like to introduce you to our ultra-thin micromodule product offering. So let me explain why this version of our micromodules came about. And no surprise here, the answer is space. Our users of this product family, micromodules in general, had basically run out of all their available space on the top side of their PCBs, but they still had some available area on the underside of these boards. While discrete components have traditionally been mounted on the underside of these PCBs, getting a power conversion solution to be placed there with a nominal 2mm height limitation, mainly due to a lot of these cards being hot pluggable, was not common. Therefore, we developed a micromodule with a 1.82 to 1.9 maximum height limitation. And as you can see from the left hand of this slide, these ultra-thin micromodules can be 50% less or even more than the height of our regular higher power devices. As an added bonus, these ultra-thin micromodules can easily be placed next to the large-scale digital ICs that normally populate these boards, and these would include FPGAs, ASICs, DXPs, and so on. And so they can also potentially utilize the heat sink that's on those types of digital products for cooling purposes for the module if it's needed based on what its power levels are. And you can see an example of this in the bottom left corner of this slide. Now, I would like to share with you some part-specific information. So on this slide, we have the LTM4643. This is a 4 to 20 volt input capable quad channel synchronous bus converter in a micromodule device form factor that is only 15 millimeters by 9 millimeters by 1.2 8 millimeters, therefore it's ultra-thin. Each of its outputs, that's the individual 4 channels, can range from 3.3 volts down to 0.6 volts with 1.5% total output voltage regulation and have independent control with virtually no crosstalk between any of the channels. Furthermore, its channels are gangable and allow for many permutations of its channel output configuration as well as its current level permutations. So these are 4 times 3 amp outputs, 3 outputs of a single 6 amp and 2 3 amps, 2 outputs of 6 amps each, or a 3 amp and a 9 amp output, or even a single 12 amp output. This allows one part to be used across multiple platforms and allows economies of scale for those purchasing guys. Okay, on this slide we have the LTM4644. It's similar to the LTM4643 except it has 4 channels and each of the output currents can be as high as 4 amps. So once again, like the 4643, its channels can be configured in many permutations for design flexibility. The size of PCB area is always a concern for the applications that we get asked to bring solutions for, and this is where a micromodule regulator solution can bring a significant advantage in board area savings versus a discrete implementation. This slide illustrates the size differential of using 4 individual monolithic synchronous buck converters, in this case our LTC3605, versus a single quad channel micromodule. As you can see, the total PCB area required by the 4 LTC3605s is 900 square millimeters versus a mere 240 square millimeters for a single LTM4644. This is a 73% reduction in PCB area. Earlier in this presentation, I talked about different methods to dissipate power lost as heat out of the micromodule package. And one of these methods was to utilize a component on package configuration. This slide helps to understand how that attained. And there's going to be 2 micromodules used for illustrative purposes here. On the left-hand side is our single output LTM4636. And you will notice that the internal heat sinks used for pulling heat out of the top of this package are on the top left. This is then over-molded and the inductor is mechanically and electrically mounted and connected on top of the package. This allows for improved thermal performance even though through the top of the micromodule package. On the right-hand side is our dual output LTM4678, which is soon to be released. And you will notice that the internal construction is similar to that of the LTM4636, except that in this case it is a dual output device. Like the LTM4636, the inductors are on top of the molded construction for an improved thermal path to pull heat out of the top of the package, where airflow of 200 LFM or more can be used to cool the device. Well, I think we're all aware that the very large-scale integration of digital ICs is continuing down into the deep sub-micron wafer fabrication path levels, with 28 nanometer already shipping and FinFET capability not too far in the distant future. Nevertheless, We have micromodule regulators that are released or currently in design that will be able to meet the demands of these digital chips. Anaroグディバイス Inc. has been supplying micromodule regulator solutions to power large-scale digital ICs since 2009, independent of their source of manufacture. Furthermore, we have worked consistently with many of these suppliers to get our micromodule solutions onto their FPGA reference designs so that the right power levels and space constraints are met. We continue to work with them on their future power needs so that our customers, that's you hopefully, can have ready-made solutions once these newer FPGAs, GPUs are released. We have software tools available downloadable from our website, which include LT PowerCAD 2 and LT Spice, to facilitate the easy and quick designs of device configurations needed to correctly power these large-scale digital ICs. At the same time, we are cognizant that we must continue to make them better and smaller while also ensuring their cost effectiveness. You can see an example of a densely populated board on the right side of this slide. ADI has worked tirelessly with FPGA and processor manufacturers to ensure the correct powering and operation of their respective digital ICs. This slide provides an example where actual applications boards have been tested and verified by these board suppliers, and this allows users to simply cut and paste these reference designs into their end product with the foreknowledge that they are guaranteed to work. So this next slide identifies our future product roadmap for micromodule regulators with power system management or PSM capability. Please note that the LTM 46, 75, 77, and 76 are all released. The LTM 4678 is going to be a dual 25 amps per channel or a single 50 amp PSM micromodule, and it will release in the next month or so. Future releases will follow thereafter and will include the LTM 4688, which is a dual 30 amp device or single 60 amp output micromodule regulator, and the LTM 4700, which we have already discussed, will release in the July timeframe. The LTM 4678 will be our first dual output digitally adjustable micromodule regulator with 2 analog loops and a digital interface for easy control and monitoring. Its input voltage range is going to be 4.5 to 16 volts and will allow outputs as low as 0.5 volts with plus or minus 0.5% maximum DC output error over temperature. It will be released in a 16 millimeter by 16 millimeter by 5.74 millimeter BGA package. This slide shows the next generation 48 volt bus power architecture, where a nominal 48 volt telecom rail needs to be stepped down in a single stage conversion process to a voltage somewhere between 5 and 0.5 volts to power various large-scale digital ICs commonly found in these types of systems. This task is made even more difficult since operating currents can run in hundreds of amps in some instances. Furthermore, in many cases, power system management is needed for system flexibility and long-term reliability. So how can this be attained? So ADI's LTM 4664 has been designed to meet this nominal 54 volt to core demand in a single stage. It has a wide 30 volt to 58 volt input voltage and can deliver output voltages as low as 0.5 to 1.5. It can also be used as a dual 25 amp per channel configuration or as a single 50 amp output device. Conversion efficiencies as high as 89% are attainable when stepping down from 54 volts to 1 volt at 50 amps output current. It has plus or minus 0.5% output accuracy over line load and temperature. It has a PM bus I2C compliant serial interface for control of core output voltages. It has digitally adjustable loop compensation with 16-bit telemetry readback that includes input voltage, input current, output voltage, output current, temperature, and faults with non-volatile logging. Please contact your ADI sales representative for more information on its availability. Thank you for watching. Please be sure to visit these listed URLs on this slide for further information. And with that, I thank you for your time. Over to you, Chris.
So let's move on now with our first question for Tony. Tony, these micromodules provide a complete solution, but how much do they cost versus, say, a discrete solution?
Well, that question gets directly to the heart of the matter. Look, there is no question that a discrete power supply solution, which typically consists of a controller, external MOSFETs, and inductor, capacitors, and resistors, would cost less than the price of an equivalent micromodule regulator. However, this requires a high degree of power supply design expertise and know-how to complete. Furthermore, once designed on paper, the components need to be determined and then sourced. A circuit schematic must be done as well. And once the layout is even completed, the components need to be mounted and soldered onto the board. Then it needs to be debugged in the lab to make sure its performance is as expected. And if this doesn't work correctly, then potentially countless hours may be needed to determine the root cause, and then you start the cycle again. And oh, by the way, the finished system is ready for production, and your power supply is the last thing in the design that's the limiting factor before mass production can start. So, by selecting a micromodule, all these headaches go away, since all the performance is guaranteed and done. We 100% test the critical parameters for each micromodule, and we try-temp test a production lot sample. All that is needed is a layout for the pin configuration on the printed circuit board, and it's ready for mass production. Okay, so it costs a little bit more, but what is the lost opportunity cost for your company if the competition gets their product to market before yours?
All right, thank you, Tony. Our next question for you here. How can you make these micromodules so small versus a build-it-yourself power conversion solution?
Aha! A very astute question indeed. As I'm sure you're aware, most high-power conversion solutions have an operating switching frequency in the 200 to 300 kilohertz range. This means the inductor and output capacitance are high value and large form factors, also meaning that the cost and board area are increased. Our solution will have much higher density than a traditional discrete layout using much tighter design rules. In a micromodule, we typically use a controller die and discrete MOSFETs, so we can have switching frequencies in the 500 kilohertz to 2 megahertz range. If you recall, for a doubling of switching frequency, you get a halving of the inductor and output capacitance values. This means smaller and lower cost components. Correspondingly, we can shrink the overall solution size such that we can offer our micromodule footprints in a range that varies from 16 by 16 millimeters to even smaller values.
All right, thank you, Tony. It looks like we have time for maybe just one more question here. So here's our last one for you. I really like the scalability of output current that these micromodules allow. So how much current could I get at 1 volt from, say, a 12-volt input?
Okay, that's another great question. Although it is not released yet, you can use 6 of the LTM 4700s in a polyphase parallel configuration. And this is a device that we've mentioned in this presentation material. This would allow you to deliver up to 600 amps of current to the downstream load. Of course, you would need to have 200 to 400 LFM of airflow over them, depending on your ambient temperature conditions in your operating environment. And in fact, I'm told by our design community that there's really no limitation to how many LTM 4700s you can parallel, but there are some design constraints that you would need to take care of. So if you get that issue, do not hesitate to contact us.
All right, thank you, Tony. Well, that does look like all the time that we have for questions for today. Once again, we'd like to thank you for attending today's webinar, Simplify Power Designs with Micromodule Products, brought to you by Tech Online, Analog Devices, and Arrow. This webinar is copyright 2018 by Aspen Core. The presentation materials are owned by or copyright by Tech Online, Analog Devices, and Arrow, and the individual speaker is solely responsible for his content and opinions. On behalf of our guests, Analog Devices, and Arrow, I'm Chris Keach. We'd like to thank you for joining us, and we hope you have a great day.